hoping that yeah, okay. Yeah, all right. Let's talk about roots. So roots are a concept that we've already sort of been dabbling with. We just haven't really been calling it a root. Okay. We've been calling roots solutions to a quadratic equation. So that's technically it's that they're slightly different, but in practice they really mean the same things. There's a lot of different ways of expressing what a root is. Okay, so I'm going to start off. I'm gonna just throw a couple graphs up on Desmos, and we're going to sort of fill around with them. So why don't I call this? Why don't I take a look at the graph? Y is equal to, I'll do one that we know how to factor, x squared plus 7x plus 12. Oops, that's supposed to be 7x plus 7x. Okay, x squared plus 7x plus 12. If I were to graph it, that's what the graph looks like. Y equals x squared plus 7x plus 12. Now, at this point in time, if I were to ask you to graph this function, I wouldn't expect you to be able to do it by hand. That's not something that we've done yet. It's something that's kind of what's coming next, like in our next round of quadratics, like when we go for like quadratics round 2, then I'll show you how to graph them and all the little details and stuff and ways of picking it apart so that you know how to graph it. But I want to show you what the graph looks like. This shape is called a parabola. So this shape has what we would call a parabolic shape. That's kind of like how you could call something square or like circlish. The actual shape that this is a parabola. So it kind of looks like a bit of a smiley face. It's kind of pointing upwards, right? And it goes up and 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 up, right? There's no limit to how far high it goes. One thing that we do know, though, over here, is it crosses the x-axis. So these are what we would call the x-intercepts, right? The x-intercepts. Those x-intercepts are -4, 0 and -3, 0, right? Is there any way that we could have figured that out without looking at the graph? Yeah? Yeah. How would you solve it? Okay, let's take a look at this. Okay. So how could we get the x-intercepts for the graph y equals x squared plus 7x plus 12? This is a graph that an equation that I like to use all the time. Y equals 7x plus 12. Or sorry, y equals x squared plus 7x plus 12. Because I just know right away that that's something that I know how to factor. I know I can factor without even looking at it because I'm so familiar with this one. So, well, let's think a little bit about the x-intercepts. Okay, let's sort of take this apart. Remember that an x-intercept. How could we describe an x-intercept? It's a point, yeah. The point at which x goes through y. You kind of got the wording, but it's a little bit mixed up. Anyone wanna help them out? Go ahead. Yeah, the graph passes through the y. Oh wait, the y-axis or the x-axis? Yeah, because there's the x-intercept, right? The x-axis. Yeah. Yeah, and the x-intercept is a point at which the graph passes through the x-axis. Okay? Another word for this is a root. But we only use the word root when we're talking about a polynomial. So we only say root for polynomials. So far, almost every function that we've looked at has been a polynomial of some kind. So it's we don't have to worry too much about using the word incorrectly. But in general, we'll just call them roots. So a root is where a polynomial passes through the x-axis. Okay. Okay. So let's see here. So let's talk a little bit about how we could find some of these roots. So what can we say about the y value in an x-intercept? Go ahead. Yeah. Y must be 0. So really what we're looking for, for values of x that make y 0. So let's go ahead and solve that. So I'm going to copy out our equation one more time. So my equation was x squared plus 7x plus 12. And I'm saying that y must be equal to 0, right? Y must be equal to 0. So let's set y equal to 0. Okay. And look at that. There's our quadratic equation. We know how to solve these, right? So we can just factor that. We get x plus 3 times x plus 4. And that's equal to 0. Okay. And that gives us two equations, right? We've got that x plus 3 must be equal to 0, or x plus 4 must be equal to 0. Or in other words, x is equal to negative 3 and x is equal to negative 4. And look at that. It's consistent. It's consistent. I get zeros at negative 4 and negative 3. Right? Just like what we said here. Okay? So, I kind of lied a little bit. There's a slight difference between the word x-intercept and root. Okay, I lied. There's a slight difference. The x-intercept, we say that that's a point. A root, the root are these values. So there's a very slight difference. So the roots, let me just write down the roots are negative 3 and negative 4. And the x-intercepts are negative 3, 0, and negative 4, 0. Okay, so you can see there's just a slight difference. The roots are just like the values of x that give us y, whereas the x-intercepts are actually particular points on the plane. Okay, but you can see they're very closely related. Very closely related. So let's think a little bit about that. Okay, oops. Let's think about what this means. Yeah, for sure. Is that far enough? Okay. I'll give you a second. All right. Let's see here. So let's try to put let's put some of these pieces together. So here's a question. If I have a quadratic function that has been factored how can I find its roots? How do I find its roots? So I've got a quadratic function that's been factored. How do I find its roots? So in other words, I've got a function that looks like this. F of x is equal to. Now remember that even though we factor it, we may get something that looks like this. We may get like, we might have ax plus b in here, and we might have something like cx plus d, right? Where a, b, c, and d are just real numbers. Okay. So how do I find these roots? Do we know them already? Can we just look at it and determine it? Or are there extra steps that we need to follow? Is the majority of our work done? Do we have a lot more work to do? Think about that for a minute. Well, I want to find its roots, right? If I want to find its roots, I'm going to set this equal to 0, right? Because I want to know where the function is equal to 0. Okay, so if I added that one extra step, I wonder if that's going to help us at all. That ax plus b, cx plus d. Remembering that the only real variable that we have here is x. All these other numbers, these are just constants. I'm just trying to generalize so that this would describe any kind of situation that we'd be in. Are we able to determine the roots now? Mm-hmm. You're very close. We got ax equals negative b. And if we were to solve for x, what do we do next? Yeah, divide by a. So x would be equal to negative b over a. Same thing over here. Yeah, we'd have cx plus d equals 0. Cx is equal to negative d. X would be equal to negative d over c, right? So those would be the two roots that we would get as long as we can factor it. Okay? Here's another question. Can a quadratic have only one root? What do you think about that for a second? Can a quadratic have exactly one root? Not two, just one. Good question. Yeah, yeah. Starts with a T. Tangent. Yeah, exactly. Because the x-axis is like a tangent to the parabola. Yeah, absolutely. Absolutely. Yeah, excellent observation. Thing is, like, what would that look like? algebraically? What would the variables look like? What do you think? Oh, okay. So x minus 1. I'm going to sort of expand it. X minus 1 times x minus 1. Okay. And I'm also going to use the function notation. I'm going to say f of x equals. So if f of x is x minus 1 times x minus 1, well, the roots that we have would come from the equation 0 is equal to x minus 1 times x minus 1. And the only way that this is going to be true is if we have x minus 1 is equal to 0 or x minus 1 equals 0. And you can see we have some redundancy here, right? We're doing the same thing more than once. So here we would have x is equal to 1, and then x is equal to 1 again. Ah. So here we actually have a root that has been repeated. We have a repeated root. So our roots here are just 1. Okay? And we can say that this root has been repeated. Okay? So look at that. So I'm hoping that that this kind of discussion on roots is going to help with some of those questions where we're looking for particular quadratics that have. Well, I'm hoping we don't have too difficult of a time finding a quadratic that has 2 solutions, right? There's a lot of examples that you could just copy and paste from your book, right? Most of the ones that we look at have had 2, exactly 2. What am I trying to say? 2 solutions. This might help you find one that has exactly 1 solution. What about this? Okay, here's another question. Do quadratics always have roots? Like, is it possible for a quadratic not to have a root? And let's just take a look at this equation here. Or this graph rather. I'm gonna sort of hit fast forward a little bit. Okay. I'm gonna sort of show you, and I don't expect you to like fully understand this. You're not expected to write any of this down or anything like that. But in general, this is you know how like with lines we have like y equals mx plus b, right? It's like the slope intercept form. This is what we call vertex form for quadratics. I'll teach you about it in like a month. But this is basically what it looks like plus b. Okay, I'll add all these, and then with these little parameters, I can kind of flip my parabola like that. I can do all this fun stuff. I can move it left and right, and I can move it up and down as well. Okay, so let's just take a look at this parabola and ask ourselves, how many roots does this one have? It's got 2 roots, right? It passes through the x-axis exactly twice, right? There they are. And if I move this one up a little bit, it's kind of hard to get it exactly, but just like you guys mentioned before, here we have a point of tangency, right? It's tangent. The x-axis is a tangent to the parabola, in which case we have exactly 1 solution, right? Or one root rather. So here's our 1 root. There it is. Now, if I raise my parabola up a little bit, no roots. Yeah, it's been uprooted, right? It's not like it hasn't gone underground, right? It's staying above. Sort of, yeah, sort of. Because you can imagine if I had a sad face, right? And then this one has no roots either, but it's all on the ground. So you kind of think of like the x-axis as kind of being like the ground, right? But yeah, you get the idea. So yeah, like here, this has 2 roots, but if I bring it down enough, no more roots, right? So certainly we can conceptualize what the graph would look like in a parabola that doesn't cross the x-axis. But algebraically, how do we write that down? Do we have any thoughts? I think that we've all seen the answer is no. Quadratics don't always have roots. The difficulty is like the real question. How? Like what do those equations look like? Yeah. Y equals x minus 1 squared plus 3. Okay. Why not? Why doesn't this have a solution? Yeah. Yeah, so this you're kind of working on sort of like an advanced level here, which is cool, but especially because we're in an advanced class. But let's just slow down a wee bit. So we've got just in case you weren't quite following along, we've moved it over and up. Oh no, sorry, this should be 1. Close enough. There it is, 1, and this should be plus 3. Okay, so from like a graphical perspective, I'm just gonna say 3. From a graphical perspective, we can see it just doesn't cross the x-axis, which is absolutely correct. But I want to know, like thinking about algebra, just with algebra, the tools that we already have. Let's see. So this is kind of like like your answer is not wrong. Like you're absolutely right. But I'm gonna sort of work a little bit slower than that because I think you're learning some stuff. Am I right to assume that you've been doing some extra research? Yeah. Okay. So for those of us who haven't done extra research, let's try to think of an equation, a quadratic equation that has no solution, without thinking about graphing and what it looks like. Just thinking about the algebra. Yeah. Okay. Yeah. So something like so I know that we did like y equals x squared plus 7x plus 12. You're saying like what happens if we did like 11? Or no? Okay, sorry, I can't see your facial expression with your mask. Yeah, so let's think about this one for a second. So when we factored this one before, we were saying, okay, so here's my 12. I'm looking for two numbers whose product is 11, but whose sum was 7, and we just kind of did a bit of a search, right? Now, if I change this to 11, all of a sudden my choices for the factors of 11 have changed from 12, right? The only factors that I can think of 11 are 1 and 11. And 1 plus 11 is not equal to 7. Here's our problem, though. Here's our problem. So take a look at this. So I've got, so here's y equals x squared plus, what was it, 7x plus 11. Hello? Yes, absolutely. Perfect. Thank you so much. Yep. Okay, so, uh-oh. Does have roots. Let's see what those roots are. Ooh. That's not very nice looking. Let's see what happens if we multiply these two numbers together. Anyone have a calculator on them? Okay, let's multiply negative 4.618 and multiply that with negative 2.382. Tell me what you got. Yeah. So kind of accounting for rounding, those two numbers multiply to get 11, right? And what's their sum? Yeah. Yeah, in this case, their sum would be negative 7. So those numbers, we found them, they're just not integers. They're just not whole numbers. So this one, it still has, we can, even though we can't really factor it using whole numbers, it's not a good contender for one that doesn't have any solutions. Let's keep thinking. How can we come up with a quadratic equation that doesn't have a solution without overcomplicating it? Forcing it to divide by 0. That's a good idea. Although I don't know if we ever have to divide anything when we're solving, right? That's a really good idea, though. That's often a good way to sort of exploit mathematics, is try to force a division by 0. But that's not quite where we can go, I don't think. I'm going to give you a little hint. Let's try one that is of the form x squared plus a. Okay? Let's forget about the middle term. Okay? So let's try to find one of the form f of x is equal to x squared plus a. Might simplify things a little bit. So we want to make sure that the equation 0 equals x squared plus a has no solutions. How can we make that true? Mm-hmm. So if x squared is equal to a negative number, so we know that x squared is always going to be greater than 0, right? Because even if x is negative, a negative times a negative is positive, and a positive times a positive is also positive. So we know that x squared must be greater than 0. But if for some reason we say that 0 must be equal to x squared, let's say plus 1, then if we wanted to solve this, then we would get negative 1 is equal to x squared. And we know that's not possible. Okay, so that's not possible, which means, let's take a look at that function, x squared plus 1. So let's do y equals x squared plus 1. I'm going to hide these other guys. No roots. No roots. Right? So I'm hoping that this discussion on roots is going to sort of help us out with some of the assignment questions. They were intended to be, thinkers, ones that you really have to sort of do a bit of a deep dive. I'm hoping that this will help. But what we like, the real take home should be that for a quadratic, we only have 3 possibilities for solutions. We should only be able to have either 2 solutions, which we've seen a lot of. Most of the ones that we see have 2 solutions. We could have exactly 1 solution, like if it's something squared, right? So like something like this, which would be, f of x equals x minus 1 squared, right? And then they could also have no solutions. And there's many different ways of seeing ones with no solutions. But the essence of it is that you can't take the square root of a negative number, right? Okay, so I'm going to end the video there. And for the remainder of the period, we're just going to have some